finding this lecture theatre is a nightmare.
Yeah, oh, hello. Yeah, I know. I had to put a map out on the... Okay. We have a full house. How exciting. We'll see how long this lasts for. So just before we start, Tammy and Gab, is audio working? No, we'll do introductions later. But is audio working on the stream? Can you hear me on the stream? Because I can't see the chat. Okay, fantastic. I can't believe everything's working.
Can you turn it up louder?
A bit louder? Okay, let me see what I can do. How's that? Is that better? Too loud? There's a little delay. Think it's fine. And everyone in the room can hear me, especially, what have we got, the balconies up there? Look at that. It's like the elite society gazing down upon us. Okay, I gotta say I'm in disbelief that everything is somehow working, but this is a very good thing. Okay, one thing that's not on the slides before we start is that it's surprisingly, so a little bit of noise in the room can sound like a lot of noise to some of these mics. We don't have someone like Sebastian doing proper mic setups for us. So especially when we're doing sort of technical content, if we can keep the noise, I'll give reminders, but excitement is good, but it can sort of make the stream and the recordings a bit hard to hear, but we'll be looking to improve everything as we go. Okay, let's do a brief overview of today's lecture, our very exciting first lecture. We have a lot to talk about today. It's really exciting. Sometimes it's nice to just get a brief overview. Also, this setup is actually quite nice in here. I'm very happy. Oh wait, is the camera working? Oh, the camera's working. Okay. What a shocker. So we will do a little bit of overview and admin of the course, just because is this first? That doesn't make any sense. Of all of you here, is their first lecture at UNSW? I would say that's just approaching half. That's so exciting. Welcome to UNSW. Welcome to maybe CSE, maybe engineering. Maybe you're taking this as an elective, although in first term, maybe not. Maybe some of you are veterans who's like, been here, done that. Let's just get this over with, Jake. No one's? Okay, that's good. So because it is your first term, it's really important. We'll do a little bit of overview over what happens when things are going well, maybe when things aren't going well, who to contact, how to get help, and all of that. But then most of today's lecture is going to be really exciting, talking about some content. So who watched the welcome video? Did you like it? Did anyone understand what it was referencing? I feel like the reference was lost maybe. It's the Vogue videos. Okay, cool. You can talk to me anytime on campus if you see me about tennis, coffee, programming, software, I don't know, whatever. Melbourne being the superior Australian city. Okay, these images cropped really nicely. We have a massive team that leads this course, and it's really important we shout them out because it's not me running this entire course. So we have 3 course admins that you can just see glimpses of. This resolution's a bit strange. So Nicole, Rory, and Tammy, they are awesome. Tammy's over there in the corner. You'll see a lot of Tammy. We have lecture moderators. There's no photos because I wasn't 100% sure who was coming, but Gab's here today, and Gab will be here all term for lecture monitoring, and Tammy will be replaced. But you're irreplaceable. And then we have, this is just whoever got lucky enough that I could find their photo easily. We have something like 50 tutors that you'll meet in your tut labs this week. Go to your tut labs, meet your tutor. They are all awesome, they're all amazing, and they're going to be your best friend as you learn programming 1511. So that's enough about us. We can't wait to meet all of you. Why don't we take a couple minutes to, now we can make a bit of noise, turn to your neighbour, introduce yourself, maybe say we're not doing icebreakers, but just say hello. And if you're in the chat online, you can do the same thing. in typical, the balconies, you're not socializing, come on. If you don't mind, that's awesome. All right, we could spend, oh God. Hello, hello. Hello, 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 hello. All right, everyone. Is this mic working? We could spend 2 hours talking to each other, so we got to cut it there. I can already see. Quiet, quiet, quiet. I can already see in typical YouTube chat fashion, the chat gets a bit iffy sometimes, but it's a lot more polite in the room. But welcome everyone. This is a lot of your first term, maybe second, third, or it's your first comp course you've transitioned in. So we really want you to make a few friends, talk to each other in your tutes and in the lecture as well. So it's important, if you see familiar faces, be brave, go say hi. Everyone's in the same position here. All right, the boring part of the lecture, but we should do it. I got a few emails the last couple of days. Jake, there's no Moodle page, what do I do? Well, that's our blessing that there's no Moodle page. So we have our own course page. Who's accessed it? A couple people. So it's this weird URL. I recommend you just bookmark it, but trust me, in a couple of days, Google Chrome or whatever browser you use will recognize that you're going there all the time. So this is the course page. It looks something like this. And this is your home for COMP1511. Everything you need to know is linked or available on this site. You can, in fact, just Google CS1511 23T3 and usually this page pops up. So it is a good time maybe right now to access it and just give it a bookmark. You can find everything here, the course outline, the timetable, there's setting up instructions, which are really important and hopefully some people maybe have already had a look at. The timetable, and then down here, hopefully you have a better resolution than I do at the moment, you'd see the week-by-week content and all the tutes, the labs, the lecture slides, the lecture URL is all in this week-by-week tab here. Assignments will be here and some other resources down the bottom. At the top are some really important tabs, so important we pin them. The forum, which we'll talk about in a second. It's really important that, once this loads, let's just pretend that loaded. Maybe that link's broken, we'll fix that. Who's accessed the forum? The forum is so important. Last term we had 2,300 questions and answers on the forum. The forum, we'll talk about the resources available, but the forum is so important. We don't use Moodle, so don't stress if you don't have it or whatever. Okay, and this isn't too exciting, but the course outline's moved, but it's just linked on the homepage of the course site. We should talk about it for a second, I guess. The course outline is sort of our contract to you about how we're going to execute this course. That was a very dramatic word, execute. But you can see all the details on assessment, the schedule, you know, how much, if you've got a question about how much a particular assignment is worth, the course outline has that information. And don't worry about remembering this extraordinarily long URL that's a very human design. Just oops, just click course outline on the homepage. So if you're wondering where that stuff is, if you came from a Moodle course, well, that's not the right thing. If you came from a Moodle course, that's where you'll find that information. Okay. Another piece of information you might want to write down is the course email, cs1511@unsw.edu.au. Now, just something to point out here, don't email the course account with programming or technical questions, like my program doesn't compile, why? That's what the forum's for. You might want to email us if something's going on and you can't make your classes, or you've somehow lost access to all the systems, something administrative issues. If you've got enrollment issues, like, hey, Jake, I need to switch classes because my dog sitter's no longer available on Monday, and that's a big problem, you want to contact the nucleus and they can help you out moving tutorials and things like that, or just in general in your other classes as well. And if you happen to have an equitable learning plan, you can email that to me directly. Cool? I spoke about the forum. The forum is your best friend. You can make threads with your questions if you're stuck on something. We don't condone it, but if it's 1 or 2 a.m., you'll probably get an answer pretty quickly, maybe by another student, and then eventually by one of the tutors. We pay a number of tutors to monitor the forum and answer all the questions, and all of the questions get an answer really quickly. You can see it's already started. So use the forum. I didn't want to bore you with a bunch of other admin stuff. There's more information coming, help sessions, revision classes, and much, much more support for you is on its way. So keep an eye out for that. So as a quick recap, you want the course page and you want the forum. So how we will deliver this content to you, we have the weekly lectures. Here we are today. There's a bit of a major caveat about that I'll talk about in a second. You got your weekly tute labs, or your 3-hour tute followed by a lab. In CSC, those are always joined together into a single 3-hour block. It's the way they're designed. So you want to make sure you know where that is this week and you're ready to go. We've got some assessments as well. Okay, this is really important. So for various reasons, some stuff that marred me last term and some other things happening this term, I'm trying a new lecture sort of format. So I'll be keen to get some feedback on it. Things can change if it's favourable or not. So COMP1511 always has 2 weekly lectures. Both of them typically are in person, unless of course there's a major pandemic swiping through the world. But lately they've been in person. But we got graced this term by getting the worst lecture allocation possible on Monday and a Friday, which is really exciting. But it's a problem because everyone misses out on the second lecture by the time you go to your tutorials. So here's what we're thinking. The Friday lecture, right, will be in person in Ainsworth GO3, that's J17. The Monday lecture, so today's lecture slot, we'll do an online only lecture. So you can just watch it on the YouTube live stream. There's a number of reasons for it. If you're curious, we can discuss it on the forum or something. It's not just the timetable, it's stuff to do with this actual theatre and the equipment. But we got a lot of feedback last term that students have really long commutes and stuff like that, and coming in twice for 2 hours just on its own is a bit rough. So what do we think about this? Does this sound okay? So you get your in-person lecture on Friday, and then Monday's online. And we're flipping it. So the Friday lecture is actually going to be the first lecture. That way there's only 2 days between the 2 lectures. Does that sort of make sense? Anyway, we're trying to deal with the best that we've got. There's also a number of benefits for me for writing code online. It's much, much easier than here. Okay, but we'll see how it goes and we'll respond and we'll get feedback. Thank you, Apple. I already spoke about that. All right, I'm not going to go through all the assignment details, but here's just some pro tips that I say every single term that maybe some of you listen to, but not everyone. You can get all the actual details about the assignments online, but here's some of my pro tips for the assignments, even the labs as well. Okay, number one, start them as early as possible. Don't start them the night before they're due. You'll be in a bad spot. Don't cheat. We'll get you, and we'll make it look like an accident. No. And assignment 1 and assignment 2 are worth 20 and 25%, and those are the due dates. So plan ahead accordingly, and start them as soon as they're available. That's all I want to say on that. Okay, and what do you do if something's not going well? You're sick, there's something happening in the family, your dog's not well, or your cat. You need to travel back home, whatever. Most of these you can let us know, you can email us, but most of the time we're going to tell you you should get special considerations. So if you don't know what that is, it's a university service where you say, hey, I'm not feeling well, here's a medical certificate, and then they'll come back and say, hey, that's not good. We've organised with Jake that you can get an extension for the classes this week, something like that. So if anything's not going 100% right and you need a bit of extra support, of course you can let us know, but you might also want to go straight to special considerations. And finally, a code of conduct. We usually don't need to worry about this, but we're all here to have a positive learning experience. Some of you have come from high school, some of you have gone out into the workforce or experienced a bit more of life than others. But no matter what, we're here to support each other, we're here to support you, and we don't tolerate any unbecoming behaviour. We want all of you to be people we would be proud to have in the School of Computer Science and Engineering. So no discrimination, no inappropriate behaviour, no harassment, bullying, aggression or sexual harassment. It doesn't come up much, but it's really worth pointing out. And if you see something that you think, hey, this isn't quite right, you don't have to intervene, but you can let us know and we can intervene. So feel empowered to take action if you see something that's not quite right. All right. And just a quick note on the fine line now that's sort of getting thinner, I think, between plagiarism, cheating, ChatGPT. We get a lot of questions about this. Plagiarism, using someone else's work as your own, is not allowed, and we have many different ways of detecting it, so don't do it. Your tutors might talk more to you about it. We have an official stance on AI tools like ChatGPT. You can go read it, it's in the course outline. To summarize it, we don't mind you using it. In fact, in some cases, we encourage it. However, every piece of code you submit to us, you need to be able to stand behind and explain it, right? And understand it. And it's really important because at the end of the term, you have a final exam where you have no internet access. So if you just use ChatGPT all term and become really reliant on it, you'll be in a bad position for that exam. We encourage you to work with each other. Again, the same policy applies. Everything you do, everything you submit, you should be able to stand behind it, explain it, and defend it. Okay, I actually don't think we need a quick break. We'll do a quick break later. All right, that's all the admin stuff. I know it's really boring. I don't like doing it, but otherwise we get like 200 emails asking the same question over and over. How are we all feeling? Good? We keen to actually get into some content? All right. You're at UNSW studying. Who's in a computer science degree or a degree within the School of Computer Science and Engineering? Wow, a lot of you. That's fantastic. Maybe engineering? Anyone in an engineering? That's probably the rest of you. Who's in something else? Anyone want to yell out what you're in? Business. So this is an elective?
Yeah.
Are you?
I'm thinking about it.
Business. Anyone else in something else? Or you can yell it, but yeah. So a lot of you have a computing or at least an engineering interest and background. And so you've probably been in the world of programming before, right? And there's so much to talk about. It gets overwhelming. Computers, compilers, programs, C, operating systems, Unix, Linux. What's the difference? Jake, what's going on? And so part of COMP1511, of course we teach you the programming fundamentals, but we really teach you the fundamentals of a computer and the way it all works and comes together. And that's a really important fact. There's a lot of introductory programming courses at worse universities that just teach you programming. They teach you how to write code, maybe in Python or whatever. That's not really so much what we're interested here. We want to teach you how it all comes together, the foundations of computing. That's why it's called programming fundamentals. It's not called software engineering or programming. So we come back to this really important question. What is a computer? You've all got one. It looks like all of you have one in front of you. Who wants to take a guess? Not a guess. Who wants to give an answer? There's no...
A machine that runs mathematical operations.
A machine that runs mathematical operations. That's interesting. And I don't disagree. There's a really tight coupling between programming and mathematics. And oh my God, this is the camera I'm using, but there's one in the... Sorry, look at that. I should have just... Okay, maybe this room's good. Anyway, do we have some lecture chat? Someone said cough, cough, UCID. The YouTube people are always unhinged. You guys are much nicer in here. Anyone else want to have a jab at an answer? You've all got one.
A machine that executes programs, follows instructions, and stores information.
So I'll just repeat it for the mic. A machine that executes programs, follows instructions, and stores information. I like that. The answer I had written, in fact, if you go look at the lecture notes, which I should describe briefly, there's my answers under there too. My answer is that, yes, you're both 100% right. They are these machines, they're amazing things that execute instructions, but the key is they're configurable and they're reconfigurable. They don't do the same thing over and over and over and over, right? Every day you open your computer, you might get a software update. You want to browse the web, you download a browser. That's a new set of functionality now. You open the calculator, now your computer's a calculator. What makes computers different from all the machines that came before it, and there were plenty of machines that came before it, is that it's configurable. And the configuration, in quotes, is humans like yourselves writing programs for the machines. That's really important. So we say we're writing programs. What's programming? It's those sets of instructions and data, so you are very good to say data, that's part of it, that achieves a task. And that's what makes computers amazing. Because someone can come along and say, I've got this computer, it can do all these things, but I want it to do something that it can't do at the moment. And in a previous paradigm, right, you just say, oh, you've got to build a new machine. But we can make our computers do whatever we want. So I'm not actually a huge fan of analogies with programming. I think they can get overused, but you can sort of think as writing programs as writing recipes, right? You're providing the steps required to solve the task. Your computer executes these steps for you, right? So usually some other human is maybe delivering a recipe, but in this case, the computer executes the recipe. And if you make mistakes in your recipe, well, you're going to have a problem with your final result. So these machines are sort of like these weird robotic chefs that can deliver your recipes for you, which would be really nice, isn't it? So you write these recipes, you write these programs. There's so many of them. How many programs are sitting on your machines in front of you? Hundreds, thousands, some of which came with the operating system, some of which you downloaded. How does this all work? How are they all running at the same time? Does anyone know? It's on the next slide, so you might have peeked ahead. Anyone want to yell out the answer? Who manages all these programs on your computer? It's not the CPU. Someone said it, the operating system. So if you imagine this computer is a kitchen and it's at the same time, simultaneously, it's building all of these tens, hundreds of recipes at once, it would be a massive mess, right? Could you imagine your kitchen if 100 people were trying to bake a cake or something? It would be, I bake one cake on my own, and it looks like a tornado hit my kitchen. So we need a head chef. We need some key figure that manages it all, and that's the operating system for computers. This is important because if computers weren't configurable, we wouldn't need an operating system because it would just be doing the same thing over and over. So an operating system, it's the interface between the user of your computer and the hardware of the computer. It manages heaps of things. It's extremely important. Who's got a Mac? Maybe half of you? So what's your operating system? Mac OS. OS stands for operating system. Some of you have Windows computers. It's in the name. Who's running Linux? The hardcore. No, no one? Not one person? You? Maybe not with you today, but in general, yeah. There's lots of different Linux operating systems. They make sure programs do what they're supposed to do. And this really cute looking guy, he's actually quite, don't underestimate him, I would say, but he's the mascot. Anyone know his name? Not Pengu. Say Pengu. That's a throwback. No, anyone know his name? His name's Tux. And he's the mascot of the Linux operating system family. And you're going to get really familiar with both him and the Linux operating systems. Linux operating systems are everywhere. Billions and billions of devices every day. You're using it all the time. Maybe you just don't know. And they are also desktop operating systems. So you've probably heard of Ubuntu before. They're open source, which is really nice for us. So we can see how everything that they do, we can sort of see the source code. That's not the same for Windows and Mac OS. They're reliable, lightweight, secure. They're really fast. They're amazing contributions. And you're going to be using Linux all throughout COMP1511. And you might be asking, Jake, I don't have a Linux computer. We'll get to that in a second. Do we have any questions on anything so far? Let me quickly glance at the chat. Okay. So, anyone know what these two movies are? One of them is more obvious than the other. Yes, it's one of my favorite movies. The one on the left, does this work? No. The one on the left is a movie called Hackers, came out in 1995. Angelina Jolie's, it's like her first film. It's a great movie. And the one on the right is The Matrix, yeah. And you often see when you look at these, you know, obviously they're very cringy now maybe, but you look at these movies and you look at other programmers, and they're often typing instructions in this sort of black and green weird window that if you've just been using your computer, you're like, that's not how computers work. I click buttons and I move the mouse around. And so now we're becoming programmers and we need to interact with our computers in a way programmers do. So let's introduce a few really important topics, and then we're going to jump into a demo, and you can follow along that demo and get your hands on, or you might be able to follow along the demo. We'll see if everything's downloaded and stuff. So, developers, systems people, we interact with our computer through the terminal. Some of you maybe have used one briefly before to do some sort of weird task that you couldn't do with a GUI, but all the terminal is a way to send text-based commands to our computer. One way to think of it is that when you click a button in Mac OS or in Windows, under the hood, it's all working through this terminal. In fact, the early computers, right, before Windows came out with its graphical user interface, this was the only way to interact with computers. And it's a way that you're going to start interacting with computers. So before we do that, let's go over some terminology. It's really important. So this is the terminal. It's an application, it's a program that is a graphical program. You can drag the window around. And in it, there's some text, basically. The terminal hosts what we call the shell. So the shell, there's lots of different shells. In COMP1511, we'll be using Bash. I use ZSH. macOS actually defaults to ZSH now, but that's a bit of a minuscule detail. So the shell is a special program that runs within the terminal, and it handles all of this interaction with the computer via text. It has its own syntax, it returns output, and it draws that output back to the terminal. It's really important. And we've got the prompt. It's that sometimes it's a different color, sometimes there's a $ somewhere on it. Different prompts look different. The prompt is part of the shell, and it displays the line of text that gives you back some information and then waits for you to type information back to the shell. So they're the three major components of the terminal. So how do we use this thing? And then after that, we want to talk about why we use this thing. So now, that's going to be annoying if I can't. Anyway, if you go to setting up on the course page, and click that first box, we have a bunch of instructions for you on how to get set up. Now, remember I said we're going to be using a Linux operating system, but you might not be running Linux on your computer. That's okay. So by our good nature, we actually give you, in the K17 building, the home of computer science and engineering, each one of you gets your own Linux computer, Linux-based computer. And you can remotely access it. It's really cool. Now, to remotely access it, you need to follow these instructions. Some of you have maybe already done this. So right now, in fact, we should take the time to do it. We've got time. If you haven't done it already, of course, go to this page and download this application called Tiger VNC for your operating system. For most of you, I don't think anyone's got 32-bit computers anymore, so you want to get either 64-bit Windows or Mac OS, depending what you're using. Download that application and install it. And what we'll do, as you follow along, chuck your hand up to give me an indication as to when people are starting to get up to the next step. Now, I've already done it, so I'm not going to do that, but you'll download it, install it, and you'll get something like this. And in the meantime, I'm going to try and figure out how I can get rid of this window that's... Hide? Fantastic. The lecture slides are incomplete, tell me? So who's downloaded it? Yep. And you install it. There's some instructions there, and you should see a window like this. How do I turn this thing off? And what you want to do, once you get to this window, the instructions are on the website. You want to type in vlab.csc.unsw.edu.au:5920. But you can just copy and paste it into that server there. I'm going to go take a look at where everyone's up to. Sorry. We'll do it. All right. So once you've done that, if you've had problems, it's okay. We'll help you after the lecture. You click connect. You get to this window. You just enter your ZID and your normal ZID password. Get some warning that you should read, and you get access. Look at this. This is the Debian operating system, a version of Linux, a variant of Linux. This is a full computer running within your computer. It's kind of cool. The reason this is really important is that all of you have the exact same environment, the exact same operating system, the exact same versions of all the tools, all ready to go. So if you get this window, who's got this window open? Oh, fantastic. There we go. All right. So now what you can do at the bottom, in fact, let me make this full screen. At the bottom, you see that beautiful green icon there that says the terminal. You click that and look at that. You've now got a terminal open. And we can pause there and go back to the slides. Okay. So how do we use this thing? And maybe more importantly, why do we want to use this thing? So let's play around with it. So there's a bunch of commands. Remember, every way you interact with the terminal is via text. It's basically instructions via text. So one thing you can do is the ls command, which stands for list. So you can type ls and press enter, and it lists all of the files within this current directory. That's pretty cool. It's a text-based way of opening a folder, right, to a directory. There's other commands. You can make a folder or make a directory using the command mkdir. You might say, Jake, why are they named in this weird way? It's just the way it is. Someone decided it a long time ago. So you use make dir, and then you give it a directory name, and it will make a folder. So we can say make dir hi 1511. Now it doesn't look like it did anything, but in fact, in the world of Unix and the world of Linux, no output is generally a good thing. It means it works successfully. And to prove that, I can list again, and you see there's that directory we just made. So something that you can all do right now is create the directory that you're going to be working from in COMP1511. People prefer to do different things. Some people prefer to make a code directory. You might want to make a COMP1511 directory, whatever it is you want to do. So you can make dir COMP1511. You can call it whatever you want. In general, you can have names in directories, but it's better to not. So we put underscores or something like that. So you can say, also, is this, can you all see it? Is it big enough? Okay. So you can say make the COMP1511 code, or just code, or you can call it whatever you want. Now, I'm going to do something slightly different, but you follow along. Okay. So you've made a directory, you've named the directory, but if you notice when you type ls, you're not in the, you haven't opened the directory, right? So how do we open that directory? It's on the slide, but someone want to yell it out? CD. It stands for change directory, and you give it the name of the directory you would like to move into or to open. So this is like double-clicking a folder in Windows. So you can cd space and the name of that directory you created before. I'm going to go into a special place because all of the code I write, I want you to be able to access it. So I'm putting it in a special location that you'll all be able to access. But you don't have to worry about this. So I'm going to cd into public HTML. CD into, and you can do multiple CDs, right? You've got multiple folders. CD into 23T3, make the lecture code. I'm going to CD into lecture code. Now you might be thinking, well, Jake, that was a bit fast for me. That's okay, you'll get used to it basically. But the point is I've CD'd into some directory that I made and I want to work from. me just put this here. All right. Now, if you need a bit more time, just put your hand up or something and let me know. If you're in a directory and you're thinking, hold on, I'm a bit lost here, I don't know where I am, there's a command called pwd. Does anyone know what that stands for? Someone yell it out? Print working directory. Print the current directory that I'm in. So I can type pwd, press enter, and it tells me, hey Jake, you're in this location. So this is a way that you can verify that you're in the right place. So there's some really important commands for you. Now you might be thinking, Jake, this is cool, but why would anyone want to do this over just clicking a folder and right-clicking and clicking new folder? And the reason becomes clearer. Those are how we move around, delete files. This is really cool. So I don't think we're going to do any of these right now, but this is maybe good as a cheat sheet for you to come back and look at. So if you want to copy a file, you use the cp command. If you want to move a file, which means, to cut and paste it essentially, mv. rm is remove or delete. And if you want to copy an entire directory or a folder, you use cp or mv the same way you usually do, but you can give it a -r, which stands for recursive, which just means to copy the entire contents. So this is more of a cheat sheet slide. That was talking about VLab. Okay. Now you might also have noticed that I have some nice colors on my terminal and you don't. Are you seeing that? Maybe? Yes? Some nodding. So that's because we make some nice config for you to make the terminal a bit more friendly. And so to get that, all you have to do is type 1511 space setup in your terminal anywhere, in any directory, hit enter, and I think it might, does it ask you some questions, Tammy and Gab?
Installing extensions.
It just does it?
Yeah.
Yeah.
Oh.
I mean, I've already done it before, that's why it might not. Yeah, okay, so it just does a bunch of stuff. I'm going to just go cancel, but for you, I think it just installs it. Yep.
Give me all this.
Yep, cool. So you get some nice colors and a lot of different changes actually to make your environment a little bit more friendly. Again, if you didn't bring a computer to the lecture today, that's okay. You can follow along all of this in the first lab or at home. All right. Okay. So we have some tools. We've installed some tools. Can we write out our first program yet? Are we ready? We're almost ready, but I think it's time to sort of talk about a bit of context around what we're doing. So remember I said we want to not just teach you how to write code, we want to teach you why it works and why and how computers work. This is really what sets us apart from many other universities around Australia. We go low. We do things maybe sometimes the hard way, but it's always worth it. Okay, so let's take a step back. These computers, all of them, a Mac, a Windows, an iPhone, an Android phone, whatever. We said they're machines that are configurable and run precise instructions. Now these instructions, you might be asking, well, what do they look like? And this is sort of what they look like. Who knows what that means? It's binary, but what is it? What are the instructions? We have no idea. It's not well, maybe someone can, I don't know, probably not. But this is the language of the computer. It's zeros and ones. We probably talk about, that's sort of in pop culture at the moment, like, computers run in binary and zeros and ones, but It's really true. You've got to understand, every part of a computer runs in zeros and ones. And who knows why it's zeros and ones?
Is it like gates, like true and false?
Gates, yeah. So the actual hardware in the computers is binary based, but why is it binary based? Maybe the computer engineers in the room might. It's on or off, but why is it on or off? Because someone said it, someone said the word voltage, and that's the correct answer. At some point there's electrons flowing through the computer, and there's either voltage or current or no current. It's on or it's off. So every instruction, every piece of data, every piece of code, the computer only understands 1 and 0. We do not work that way. Imagine trying to communicate to your friends next to you, or your future friends. Imagine trying to describe your name in zeros and ones. Now, it's possible. You can learn the binary notation, come up with some agreement for what series of zeros and ones describes which letter, right? It's possible. Computers do it. But it would be a nightmare. Do we all agree? Humans can't work in this language. Or if they can, they can't do much, right? It just gets too hard. So that's a problem. Jake, how are we meant to write these programs if we can't speak the language of the computer? Do we just go home and call the next 10 weeks off? Some of you are like, yeah, that would be good. No. So these computers need precision, and this machine code is probably too precise for us humans. I think we all agree. And that's the reason why we can't just say, hey, computer, add 2 numbers together. It doesn't understand English or whatever native language you may speak. It doesn't understand what a number is. It really doesn't know what the word number means. We know what it means, but the computer doesn't. So we're a little stuck, and we need a way to fix this problem. And that's basically what programming languages are. We need to write instructions precise enough that they can be translated to that machine code, to those zeros and ones that make sense for the computer, but simple enough that we can actually have a chance at doing something. So we need a shared language, a language that's more precise than English or whatever language we might speak, right? But it's comprehensible enough that we can actually write it and that other people are able to read it. And that's what all programming languages are. And the C programming language is one such language. So C programs can be converted to machine code, but can also be written by humans. We found a balancing point. Over decades and decades, C was not the first programming language. The first programming languages like assembly, they were maybe a bit too precise. And there's other languages that are much less precise than C. But over decades, we've started figuring out what makes a programming language good for certain tasks. And in such a way, it's structured enough that it can be converted to machine code, but understandable by humans. And C is such a beautiful language. Anyone know what decade it was first released? 70, I think earlier than the 70s. I think it was the 50s and 60s, around then. Came out of Bell Labs over in America. And this is what it looks like. This is a C program. For some of you, this might look, you might know exactly what's going on because you've done this all before, and some of you, this might look like gibberish. But we'll talk more about it as we go through this course, and pretty soon this will be like a second language to you. So this language, this description, right? It uses letters that we can understand. It describes instructions that we can understand, but they're precise enough that they can actually run on computers. So let's write a C program. How exciting. So we want to create a C file using the terminal. We're going to write our program using a text editor. In this course, we use Visual Studio Code. And we're going to save the file. That's what we're doing at the moment. All right. If you have a bunch of stuff in your terminal and you want it gone, you can actually just type the command clear, and it resets the output of the terminal. So go to wherever you were working, whatever directory you decided. You might want to type pwd and make sure that you can see the directory that you think you're working in. One common mistake that a lot of you are going to make is that you will be in the wrong directory when you're creating files and doing things, and you'll get a bit confused. It's always worth, especially as you're starting out, just double checking that you are where you think you are. And then it gets really annoying when you have multiple copies of the same file and you're updating the wrong one, all of that. Okay. All right. So there's actually a few ways that we can create our first program. Here's the way we're going to do it today. We're going to type the command code, space, and the name of the file that we want to create. So I'm going to call it hello world.c. So our C programs always have the extension .c, right? That's a convention that we all stick to, so we can identify our C programs. Again, you can name it whatever you like, but don't put a space in the name. So I just hit enter, and now a couple of things is like, whoa, what's going on? But this text editor is going to open up, close up that. This text editor is going to open up, and it's got a cursor, and this is now a graphical application that we can actually type some. Look at that, I can type stuff. And you can see, I just want to quickly do something. Oh God, come on. You can see, if you look at that tab there, it's got the name of the file that we asked it to create. Now, here's another pro tip. Is this working now? Laser, I don't want a laser. Let's try magnify. There we go. Do you see that black, oh God, I'm shaking. Do you see that black dot next to the file name? That means the file is not saved. Tammy, Gab, how many times do you get a question from a student? They're like, I wrote this code and it's perfect. And I compiled it and it doesn't do what I thought it should do. And you go, there's a black dot there. You never saved the file. So always remember, after creating a file, modifying the file, you want to save it. So now we can just type out our Hello World program. And this is the program that we're going to type together. And then we're going to go line by line and explain how it all works to some degree. All right. Shall we? I'll make this a bit bigger. I'm going to go hash include, square, angle bracket, standard.io.h. For now, you're right. You're just basically, if you're not sure what's going on, just copying character for character what I'm typing. We want to go a full end-to-end program compilation. But you will understand every single character, every single line of this program. Yeah, me too, Tabby. Control S is like a built-in tick now that the wheel. All right. Now I'm going to go from memory. You can look at the lecture slide if you need to. We're going to type int main void, like that. Curly braces, something that you start to notice as programmers is that you get familiar with, and you can name every type of bracket or brace. And different people call them different. Do you call them curly braces, Gavin and Tammy?
I just call them like brackets and then just like with my hand.
Okay, that's a visual What about the top ones? Angle brackets, yeah, I call them. It's like a variant of ASL for programming. So I think I call these brackets, these braces, and these angle braces. I don't know now. Anyway, so we type this. We get here. I'm going to then type printf, double quotes, that's important. Hello, COMP1511. Now, you can type within these double quotes, you can type any message you want. So you can come up with whatever message you want to print out. So I'm printing out hello COMP1511. You can print out whatever you want. Keep it PG, please. So we're not done just yet. We're going to just type return 0 just there. Now I'm going to hit, Control S. So I just saved the file. You can see now that dot's gone and it's become an X. Right? That means I've saved the file. And to prove it, if I open, ignore that. If I click terminal at the top, I go back to this terminal and I type ls, you can see that hello world.c file has appeared. Oh, I broke my thing. Because we created the file when we saved it. Who was able to follow along? Who's still going? Okay, we'll give a couple of minutes. If anyone's stuck, you actually maybe, can you put your hand up and someone can come take a look? I think we're able to do that. Otherwise, you'll get unstuck in the week, in the classes this week. You have a problem? I can't hear you. Okay, good point. So, sorry. To save the file, you can go File, Save, or I just hit Control S, right? Whatever the shortcut is for you on your computer. And you want to go back to the terminal, type ls, and make sure that you can see that file. That's important. Otherwise, you may have saved the file in the wrong location. All right, who's ready to continue? Yep. Anyone need a couple of extra minutes? Couple minutes? For those of you who have caught up, here's the same program with some comments that just gives a high-level description of what each line does. Now, these comments aren't really, they may help you understand what's going on. They're not sort of too helpful. That's why we'll go through in more detail in a moment. But they at least describe what the line is doing. All right. So we said we'll go through it line by line. Let's do that. So at the top of this file, we typed include, #include standard IO with some angle brackets. Okay, why do we do this? So when you're writing programs, you're writing instructions, some tasks are so common that it really would not make much sense to provide those instructions every single time. So think about when you're writing a recipe to bake a cake and you want to, say, measure out 1 cup of flour, okay? The recipe might say, measure 1 cup of flour. But there's a few things involved there, right? You have to get a measuring cup, hold it in your hand, dip it into the, if we had to describe that every single time, the recipes would be pages and pages and pages, and it wouldn't be very useful. So because some tasks are so common, the C programming language has sort of baked them in so that you can just say, hey, do this thing, and even though it might be 10, 15, 20 steps, we get all of that functionality for us. Conceptually, does that make sense? I know sort of tangibly it might not, but conceptually does the idea make sense?
What is the .h?
That's a great question, the .h. That one I'm unfortunately going to say we'll talk about it in a future lecture. It's just, we write .c files. So it's a different type of file called a header file, and it just describes some things that are available for us. If you're really curious, you can Google it. Any other questions online? Nope. Okay. So there's a bunch of different common activities or instructions available for us. Now, if we want to use them, we need to include them into our programs. And that's what hash include does. So in this case, what we're saying is, hey, I want to include, and now you might be thinking STDIO, and it's not a sexually transmitted disease. That wouldn't be very nice. Anyone know what it stands for? That got a bigger laugh last time. Standard input output. Standard input output. If you ever see STD in computing, it means standard. It's this part of the standard libraries. And input output. Input output means reading and writing to the terminal. Because that's what we want to do today. All right. So in this case, yes, we want the standard input output library. This allows us to make text appear on the terminal. That's really cool. And yeah, almost every C program you ever write will have this line at the top. Because we always want to either read from the terminal or write to the terminal. All right. Now we have the main block, is what we're going to call it, or the main function. So there's a few components here. But here's conceptually what's important about this. Every C program, in fact every program, has what we call an entry point, or the point at which the program starts. And in C, that's called the main function. So every C program needs this line somewhere. And this means, hey, computer, this is where my instructions actually start. The hash include, you might think that's a line of code, but it's not an instruction. It's like, hey, I'm going to do a bunch of these things. This is where our instructions actually start. Every C program must have one of these somewhere. Could be at the top, could be at the bottom, could be in the middle. That doesn't matter, as long as it's somewhere. And the program runs in sequence, line by line, starting at the first line of the main function. So this is the entry point. In a recipe, it's just the first, instruction, right? But in C, it's this. So let's break down this function. So there's these curly braces. You see these everywhere in C. These indicate a block. So basically, the way to think of it is this main function begins here and ends here. And everything in between it was part of main. Right? It's a grouping of instructions that belong to main. And these blocks are very important. We'll be talking about them more and more throughout term. But they are how we organize code. I'm getting some nods. That's good. All right. Also, within the blocks in our actual program, we had this printf statement, or this printf call. So what's going on here? So printf is a C function, or a C instruction, that makes text appear on the terminal screen. Now, this, if you didn't have the hash include standard I/O, this would not work. This comes with standard I/O, because this is the output part. It's printing to the terminal. Anyone know what printf stands for? The print part sort of makes sense. Format, yeah, format. And who can tell me why it's print?
Because in the early computers, they couldn't see the result on the screen, it just came out half of the machine.
Exactly right. Early computers, they didn't have monitors. They had printers. So output was always printed, literally printed onto paper. Like think of like a typewriter. And this terminology has stuck with us for 5-6 decades. We print to the terminal because we used to print to physical sheets of paper that came out line by line. I mean, I don't know, this always amazes me. It's like 6 decades of, we really have evolved so much, and we're still sort of so close to it. But today, printing means something different. It means printing to the terminal. But we still use that terminology. And then you have this return 0 thing, and that one's a bit of a weird one. And to be honest, it is just it's a bit weird. So return 0 is a C keyword, so it's part of the C programming language. And it tells the computer, in this case, hey, operating system, I've finished. This is the end of the program. I'm returning back to you. Remember we said the operating system is like the head chef. It controls everything. When you start a program, you don't start a program. You ask politely to the operating system to start the program. It decides what happens. And when your program ends, it doesn't really just end. You're saying back to the operating system, hey, I'm finished. And then the operating system actually decides what's happened. So you're returning back to the operating system. And you might then be thinking, what is this 0 for then? And does anyone know? Yeah, 0 is just a convention that means no problem. As in, this program ended with no problems. It's not counting the number of problems, although that's a funny way of thinking about it, I've just realized. But 0 just means all okay. So if you've ever run a program, probably on Windows, because it's a pretty dodgy operating system, and then it crashes, and you see something pop up, and it's like error code 11357. You've all seen something like that before. That's because it didn't return 0. It returned some error code. This is the error code of the program. Someone say something? Oh, it could be any number. And different programs come up with their own decisions over which numbers mean which error. But 0 always means A-OK. And I've noticed my camera's covering the slides a little bit. Sorry about that. Now, something that might confuse you a little bit, but for now this is all okay. But if a return is in a different location, it might mean something slightly different. So what it really means is I'm returning from the current block, which we spoke about these blocks. Return means this block is finished. But if it's the main block, that means it's the end of the program. All right. And so we have some comments as well. I think this is the final component of our program. Comments are a little different. So comments are not for the computer, right? They're for us. They're super important though. They're for me to remind myself in the future what the hell I was doing in this program that I wrote at 3 a.m. and none of it makes sense. And they're for me to describe to my colleagues, this is what I was thinking when I wrote this program. But they are not for the machine. If we want to write a comment, we typically use double forward slashes. So if I go back to my code editor and I write double forward slash, this is my print statement. Now this is not a good comment because it doesn't add much value, but you can see that the Visual Studio Code makes it green to point, and it sort of gets rid of the highlighting because it's just a marker for humans. So you'll see this everywhere. It makes no difference to the program, no difference to the computer. Don't worry about the forward slash. You can do blocks of code comments, but don't worry about it. And the compiler will ignore comments, so you can put anything you want there. All right. Should we take a quick break? Let's take 5 minutes. Or maybe there's a lot of use, maybe 7 minutes. Go to the bathroom, get some water, go to a vending machine, and we'll come back in 5-10 minutes and then finish off the lecture. Sound good? Oh, thank you. Okay. How's that camera going to track me? Okay. All right. We have just under 4 minutes. Now I think the rewarding moment is about to come. Does he say so? How many is that? Compiling. All right. All right. So I have a question or a challenge for some of you, or for all of you. So remember we said that computers understand this very limited language, right? These zeros and ones, essentially. And that's the only language these computers understand. So if that's a true claim, we're at a bit of a we've come across a bit of a problem. What's the problem? Right? Because we wrote this program. And we want to run it. We want our computer to run this program. So what's the dilemma?
You're writing in text instead of numbers.
Yeah, is that what you were going to say as well? It's, yeah. So some of you know, of course. But this is not zeros and ones. This is C. The computer cannot understand this program. I think a lot of people, when they think about programming, maybe I'm wrong, but they think that this is code. This is what computers run. Did anyone think that before? You're like, no, yeah, it makes sense. Like, why do we call it code? We should just call it something else. But the computers can't understand. Your computer, my computer, does not understand this C file. So you might be thinking, what? I've been conned. What was this all about then? Okay. But remember, I also said that it's a shared language. It's precise enough that it can be converted into machine code. And the cool thing about it, if I just jump ahead here, is that we don't actually need to do much. The very smart and helpful men and women at Bell Labs that worked on the C programming language, when you're coming up with a programming language, which is a scary task, but something that some of you might actually end up doing, it's not just about deciding what your code should look like. It's also figuring out how to take the code that you've written and automatically convert it into that machine code, into that language that computers can actually understand. This is why the word shared is so important. Evasive maneuvers on the front. That's good. And that's what compiling means. Compiling means taking a programming file, a piece of code, written in this shared language, and turning it into machine code. Automatically. It's amazing. That's what compiling is. A compiler is a program. It's a program that someone else wrote. It's all programs all the way down, trust me. But sometimes we think, oh, compilers, that's something special. No, it's not. Someone wrote out the instructions for the compiler that knows how to go through a C source file and map every single instruction to machine code instructions. And we can use compilers to automate this task, to take our C code and generate machine code. And this is how we do it. Now, there's actually different compilers. There's not only different compilers for different programming languages, there's different compilers just for C. Has anyone written C before? Have you used, let me guess, maybe, were you a Windows person? Were you using a Windows machine?
I actually work on Unix.
So maybe Clang, GCC?
Yes.
GCC is a common one. And Clang or CLang is another common one. So there's actually different compilers. Different groups of people have come up with their own compiler because maybe they were trying to do something different, or maybe they were sharing it in a different way. But I bet you haven't used DCC, unless you've maybe looked at the course before, taken the course before. So DCC is a C compiler that actually was built at CSE at UNSW by Andrew Taylor. And it's a variant of GCC that does some really cool things that makes C a little bit more approachable. But you don't have to worry about that. You use DCC in the exact same way that you use GCC. Let's look at this compiler line. So just to set some context, this is happening in the terminal. So in the terminal, that's where you compile your C program. So the first component there, DCC, this is a program, the name of the compiler. So you're saying, hey, I want to use the DCC compiler. Then you have to give it something. We call it an argument, but that might be too fancy of a word. Basically the C file that you would like to convert to a machine code. So in this case, it's a program called program.c. I'm going to use the hello world.c because that's what I named my file. What did you name your file?
Hello world.c.
Sorry?
Hello world.c.
Hello world.c. So you're going to compile. You wrote it something dodgy or something. So you want to compile hello world.c as well. So whatever the name of the file that you created in code is what we'll pass to DCC. Then we have this thing here, which is what we call a flag. And it's -O, and it stands for output. And whenever you see something like this in Bash, think of it as like a placeholder for saying the thing that comes after this is the output. In this case, it's the output. So hello world is going to be the output program. And you can name that whatever you like. Typically, you name it whatever the name of the program should be. Turn up the volume. It's as loud as it can go. Can't hear the audio. Hello, hello, hello. It's okay? Okay, cool. All right. All right, so let's do that in our terminal. So we go back to our terminal. Now look at that, I've got unsaved file, unsaved changes. In that case, it was just a comment, so we don't have to worry about it. I'm going to clear it. I'm going to type ls to list out, to remind ourselves, what's the name of that C file that we created. So all of you right now, type ls, and you want to make sure that you can see that C file there. Now, if you want to be really sure that you're compiling the right thing, we can actually check what's inside this file. Does anyone know how to do that? Cat. Do you know why it's called cat? Who said that? Who said it? Who said cat? What? Do you know why it's called? I actually don't know. Anyone know? Can cat know it? Maybe? Anyway. Sometimes we just don't know. Oh, that was a bit too fast. Let me do that again. So I'm going to type cat, like meow, cat, hello world.c. And look at that. How cool. It's printing out. See, I say printing. I wasn't around in the 50s, but it's just stuck with me. It's saying, hey, this is what's in that file. So you can verify that you were right, that is the correct file. So if you catted there and you saw nothing come out, then maybe you never saved the file. Did that happen to anyone? No, you're all just too good. That's good. All right. So we're in the right directory. We've got our C file here. Jake, shut up. I just want to compile. So let's compile. Whoops. So how do we compile? Yell it out to me. DCC. Now, I'm typing hello-world.c. You type whatever you created. Now, I got to stop doing this, but did you notice I typed like 3 letters and then it just appeared? I'm pressing tab. So if the terminal is smart enough to know that if there's only one file there and it starts with the letter H, and I'm typing HE, it's pretty obvious what file I'm talking about. So if I hit the tab key, it auto-completes it. So if you see me do that, I'm trying not to do it, but it's such an ingrained habit that I can't help it. So DCC, hello-world.c, what was next? So some of you just said dash O. Yeah, don't forget the space. Space dash O. Whoops. And then what's the final component? Whatever we want to name our executable. So I'm going to name it hello world. What do I do next? Press enter. And we wait. And then we're very tense. Like, is it working? Is it not? We see no output. That might make us feel a bit unsure. But we said earlier, in Unix, in the world of Linux, no output is typically a good thing. It's the absence of error. I know it's not very kind, but...
That's supposed to print hello world?
No. It's not going to do anything. Okay, that's a great question. What's your name? Robert. Robert asked, wasn't it meant to print hello world? Was anyone expecting to see hello world there? A couple people. Okay, good. All we did by compiling was taking our C code and converting it to machine code. We didn't ask it to execute it. We didn't ask it to run it. We just created the zeros and ones that we can now run. So it's a multi-step process. And the really cool thing is that if I hit ls now, what Tammy? It is back? Oh, that's so lucky. All right. Okay, that happens sometimes. In this case, my Wi-Fi cut out. Sometimes you actually do lose connection to VLab. It's okay. We got to just get back into that directory, which is actually a nice exercise for us to do that. So who can, well, mine's a little different. Remember, I'm going to change directory, CD, into public HTML. You don't have to do this, right? This is just for me. I'm going to CD into COMP1511. Something actually, when you're CDing around, this is something I do, is I typically change directories one level at a time, and in between I type ls, because I'm just reminding myself what the new directories are. And I'm probably going to be doing it a lot faster than you'll be able to do it. That's okay. That's just experience. And then I go into the lecture code. All right. We're back. So, yeah, question?
Once we compile, do we need to do it again once we make changes?
Great question. I'll talk about that in a second. All right. So this line here is the compilation line. Compiles our C program into machine code. Now it's time to execute that executable. Again, execute is such a dramatic word, but we just mean to run it. Now, how do we run it? What we do is we do // and does anyone know what this means? Yeah, so it means look in the current directory. So we want to run this hello world executable and it exists in my current directory. That's what // means. And then I just give it the name of the executable. So notice it's not hello world.c, that's not the executable. The executable is called hello world. Now what do we expect to happen? We're going to run the program. So what did we tell the program to do? Print, I think I said hello COMP1511 to the screen, to the terminal. So if everything worked, are you ready to hit enter with me? Or have you already done it? I bet you've already done it. You got no patience. Who's not run it yet? Are you ready to hit enter together? There we go. Did it work for you as well? Okay, round of applause. That's good. That's a big moment. We compiled and executed our first. Who was that? Was that anyone's first program ever? First C program? That's amazing. The beginning of many. We made our computer do something that it has never been able to do. Yes, this program's been able to do this, but no one has ever made this computer write and run your program. You just programmed a machine. It didn't do too much. Let's be reasonable and fair about it. But you reprogrammed this machine. You got to think of it, it's really that impressive. You reconfigured the internals of a machine so that you could output this text to the terminal. Is the chatter because we're so excited? Yes? How are we going for time? Still got 20 minutes. All right, before we do that, let's talk about... Now, if you want to... so remember my Visual Studio code closed. So I'm going to reopen the file by typing code hello-world.c. And as it loads, it's a bit slow, I get that program back up. Let me make that a bit bigger. So why don't we talk through the process of reconfiguring this program, reconfiguring this machine a couple more times. So you can print multiple things. What do we want to say? Please keep it PG. You got something you want to say? No? You got, okay, sorry, I made you nervous. Tell me something, come on. Sorry? I like that actually. Cough, you said. Now, I actually think I might have glossed over this. Remember, programs are sequences of instructions. That's all they are. Don't let anyone confuse you and make it seem more complicated than it is. All programs are sequences of instructions and some data mixed in. In C, we separate our instructions with this semicolon. The semicolon at the end of a statement signifies that that's the instruction. So it's an important thing. Now, there's a bit of confusion as to where you should and shouldn't put it. For example, there's not one at the end of the hash include. And you might logically think there should be one, and you probably have a case, but hash includes aren't instructions. They bring in extra detail. You might think there should be one maybe here, but that's also not an instruction. It's just the beginning of the block. I think the best way to tackle this is you'll just learn through experience. Actually, maybe that's not true. Or let's run this. So let's talk through the steps involved. So you make a change to your program, right? We have to do a few things. We can't just rerun it. What's the first thing we need to do? Save the file. Trust me, it sounds obvious. You will forget many, many times. We save the file. I just did Control S. Then what do? Can we run it? We can't run it. We have to compile it. Exactly. We have to generate a new executable that has those updated instructions. We need to run the compiler, take the source code, and regenerate the machine code. Now you might be thinking, Jake, I've got bad fingers, I've got RSI, I don't want to type out that whole line again, it's the same line. Well, you can just hit up on the keyboard and cycle through. Oh, now because my computer disconnected, it's not there. But you can just hit up on the keyboard and cycle through to that DCC command again. But we'll retype it. DCC. So I'm using the DCC compiler to compile a program called hello-world.c and outputting it to an executable named hello world. So I hit enter. No output is generally a good thing. It doesn't look anything different here, but we assumed that worked because there was no output. You can, but you do your own thing. That's not covered. It's not within the the scope of the course. So how do I run this updated executable? Not DCC. / hello world. Okay. Hello COMP1511. It is there, right? Cough, cough, usage. And this is a public video, so they might see it. So next week I need you all here with fisticuffs to defend me. Yeah. So one thing you might be thinking, actually, who's done a bit of Python before? Who expected these two lines to be on separate lines? Yeah, because in Python and some other languages, that's what the default is. But C is a lower level language. It does nothing, well, not quite nothing, but almost nothing without you explicitly telling it to. So if you want a new line at the end of that line, you have to say, hey, I want a new line. Now, the way to do a new line is with a special character called \n, and you put it wherever you want a new line to go. Now, you might be thinking, Jake, you fool. That's 2 characters, not 1, right? I called it the new line character, but I typed 2 things. Well, yeah, you're sort of right, but \n is a single character. It's the carriage return character. We just don't have a key for it, so we have to combine multiple different atomic characters to build it, but it's a single character. Now let's say you're new to C and you're playing around with your program and you think, oh, there probably should be a Jake said put semicolons at the end, so there should probably be a semicolon there. All right, let's say we make a mistake, and that's completely fine. We go back to the terminal, let's clear it, let's cycle up and run our program again. That worked. That's a bit of a surprise. Let me make a different sort of problem. Let's say I have a typo on main. I forget the N. This is like, you're going to make many problems when you write programs. So let's see what actually happens when we do something wrong. So I forget the N there. I compile. We get an error. A very first error. This is a big moment. Error, your program does not contain a main function. A C program must contain a main function. So the compiler does many things. It doesn't just convert our programs to machine code. It also detects problems with our programs. And a good compiler is able to convey those problems to you in such a way that you can say, I can fix that. So how do we fix this problem? Add the end. Yeah, it's not that deep. There's many different types of problems that have different types of error messages. But you will come across your errors, and learning how to come back from those errors is a skill that we teach as well. So we go back, we compile again, and now I get no error message. I run the program again, and because I added those \ns, this looks a bit more like what we might have expected. Our 2 lines are on different lines. Pretty cool? This is the simplest program you can probably write. Maybe one of the most important, because it's the first program you write. In fact, when I'm learning a new programming language, one of the first things I always do is write hello world in that language. Because it means that you might think, this is a bit of a boring program, but we did so much to get here. We had to have a compiler installed. We had to learn the syntax. We had to type the file. We had to save the... It means that everything's working, and now we can go off and build amazing things. So you can play around with your printfs, do multiple printfs, do whatever you want. And I've got like 2 or 3 slides left, but that's basically it for the technical stuff. Then I thought I'll get a bit maybe motivational or soppy or something. Does anyone know what this is?
It's the first.
It's not the first computer in the world. So, online? Anyone know? Anyone know for sure? Put your hand up. No? You can guess. You don't even need to know the name. Do you know where it was? Not the Turing machine. It wasn't. Not IBM. So this is the first computer in Australia. It was called CIRAC. Does anyone know what city it was in? It wasn't in New South Wales. It was in the Superior City. I referenced it earlier. It was in Melbourne, at Melbourne University. That whole thing, I think the photo's even bigger than that, was the computer. We take for granted what computers are today, but this was the first computer. And this computer didn't run C. C wasn't invented then. In fact, people probably wrote instructions in something that looks a lot on the moon. All of these amazing technological advancements, and it's very easy to get overwhelmed and think, we can't do this. But the one thing you need to remember, these are all computers running instructions. These instructions were written by humans, just like yourself. So as you learn programming and you learn to configure these machines, you need to start thinking, what are you going to contribute? What are you going to build? What value are you going to create in the world? We'll be landing rockets, building iPhones, right? Solving medical problems. It's all computers running instructions, and that's what we're going to be doing in COMP1511. Thank you all so much. I'll see you on Friday in J17. If you have any questions, you can come down in a few minutes.
And it's a holdover from printing to
The
tape.
dots? Yeah, oh, it's a tape, yeah.
Once you print them into commit and you can't go back and change the effect, it's too late gone.
We are reluctant to change in this industry.
Great lecture.
Thank you. Thank you.
Richard goes through all this in like 5 minutes, and the only people he speaks to are like the other programmers.
Yeah, I know.
Everyone knows.
Yeah.
All right.
See you, sir. Thanks for coming.
So I have some questions.
So,
Can you upload these bigger slides?
yeah, I'll fix it.
The
That was-
other ones wasn't so good.
yeah, I'll figure that out. Yeah, no worries. Thank you.
Yeah, like when I do it, it says I can't find it. Why directory? Even though like it's up there. You can comment.
Let's hold on. Tammy, and can we get some help?
See you.
See you. Thank you for coming. See you on Friday. We're in a different thing. Okay, show me again.
Yeah, so like I try to run it forward, but like it says
Can we just start answering questions?
Okay.
Sorry. Thank you.
yeah, and it says like no file or any directory with it.
So type ls. You've got comma C, not dot C. You've made a typo.
Thank you.
So, how do you fix it? Let's put your computer down. What you want to do is move the file with the correct name.
Yes.
So I might just type it for you, but move hello world comma C to hello world dot C. This is like renaming it.
Oh, okay.
Now if you ls, you'll see it's correct. And we can compile.
Oh, okay.
Now run it.
Run it.
Yes, good memory. Hello world. Hit tab.
Hit tab.
No, yeah, hit tab now. Press enter. Well done.
Oh, thank you.
Why is it not working?
Oh, hey Jake, I just had a question. When you if you